Hello, my favorite calculus people. This is Miss Letchworth again. We're going to pick up a little bit where we left off in 4.1, and we're going to add 4.2 to it. And as we do lesson 4.2, you may be thinking, what does this have to do with 4.1? It looks nothing like it. Well, actually it has a lot to do with it, because eventually what we're going to do is we're going to take what we've learned in 4.1 along with what you're about to learn in 4.2. We're going to combine it together, and we're going to do some other topics in lesson 4.3 that puts all that stuff together. Okay? So first thing in 4.2, what I want to do is to review a little bit of pre-cal 1 with you. Alright, this is sigma notation, and we use sigma notation along with integration to help us figure out the area under a curve. So eventually we're going to get to like something that looks like this, where you have your x and y axis, there's a little curve, and say you want to know the area from where x is A to where x is B that's under that curve. You want to figure out what this area right here is, okay? Well, we combine integration along with some summation, sigma notation, and we figure that out, okay? Now, in order to do that, like I said, we're going to have to review some pre-cal, all right? So I'm going to start right here with a few examples that are actually on page 253 in your textbook, and remind you what sigma notation means. But this is the Greek letter sigma, and it means summation, and the root word of summation is sum. So what it means to do is, when you see this, it says the summation as I goes from 1 to n. N is some number. You just may not know what that number is, okay? Well, actually in this first example, they're going to tell us that n is 6, okay? 6, there we go. So what that means is we put 1 in the place of I, then we come back, we put 2 in the place of I, then we put 3 in the place of I, and then 4, and then 5, on up to 6, okay? And we add those together. That's where the summation comes in, okay? So that's what this looks like in expanded form. So this is your summation, or your sigma notation, for this particular series right here, okay? A series is a list of numbers or a sequence of numbers in which you are adding them together. All right. Now look at this one. This one says that I is going to start at 0. It's going to go to 5. So what we do is we put 0 in the place of I. 0 plus 1 is 1 plus. Now we're going to put 1 in the place of I. 1 plus 1 is 2. Then we're going to put 3 in the place of I. 3 plus 1 is 4. And then we're going to put what number am I on? 1, 2, 3, 4 in the place. Did I miss a number? Oh, yeah, I did. 0, 1, 2. We're going to put 2. There we go. 2 in the place of I. 2 plus 1 is 3. Now we put 3. 3 plus 1 is 4. Now we put 5. 5 plus 1 is... I did it again. Now we put 4. 4 plus 1 is 5. Now we put 5. That's our last number. This number tells you where to stop. Okay, and 5 plus 1 is 6. Woo, got through that, okay? Same concept here. If I goes from 3 to 7, then that means you start at 3. All right, so putting 3 in the place of I, then that is 3 squared, and then 4 squared, and then 5 squared, and then 6 squared, on up to 7 squared, okay? So that's what summation means, all right? Now, you could easily get the answer to all these numbers just by simplifying everything, you know, and saying, oh, I'm going to add 9 plus 16 plus 25 plus 36 plus 49 and all that, and get some number, okay? And that's fine and dandy when your numbers are small, but what if this were 3 to 70, or 3 to 700, or 3 to 7,000? Well, you don't want to end up with that many terms in which you need to add up. So, for that reason, there are some formulas that help you out, and they're listed at the top of page 254, okay? Some summation formulas right here, okay? So, your summation formulas and properties, okay, says that if you have a summation of some function A sub I is your function, okay, and it's being multiplied by a scalar K. K is some scalar or coefficient, whatever you want to call it. Then what you can do is you can take that scalar and you can pull it through the summation and put it on the outside of the summation and figure out what this is equivalent to. And then whatever you get, multiply it times K. All right? This property right here says, well, what if you're adding together more than one function? Maybe you've got function A added or subtracted to function B, but you want to plug I into both of them and get that summation. Well, this is the same property as what we did with differentiation and with limits. And now we can do it with summation and what we were just doing in lesson 4.1 with integration. Okay? Meaning that you can do the sum of each function separately. So you can give each one of these terms right here, or each one of these functions, its own sigma notation symbol. Okay? And break it up that way. And yes, I'm going to show you with a real problem how to use all these properties and formulas, but I want to show the formulas to you first and tell you what they mean. Okay? All right? I did not mean to go that far down. Let me back up. Where am I? Right here. This one. Okay? So, this one says, what if you're doing the summation of some constant C? That means it's just a number. The quickest way to do that, if you're doing the summation as I starts at 1 and goes to n of some constant number, is just to multiply that constant number by n. Okay? For example, let's say that you were going to do I is equal to 1 to 1,000 of 5. Okay, well what that means is you're going to do 5 plus 5 plus 5 plus 5 right on out to 1,000 fives. That little subscript of 1,000 means that that's my 1,000th 5. Nobody wants to do that, okay? So, I mean, all that is repeated addition that you do 1,000 times. 1,000 times. That means multiply, right? Times means to multiply. So your shortcuts just say 5 times 1,000. Okay? All right, now, this next one is your formula for the sum of your integers. Okay? Suppose, you're going to do the summation as I goes from 1 to 100 again. Or that, we'll do 1,000. Okay? Of your integers, okay, where you just have I right here, okay. What that means is you're going to do 1 plus 2 plus 3 right on out to 1,000. Nobody wants to do all that work, so what's your shortcut? Your shortcut is this, to remember that this number is your n, okay. And you're going to take that number and just plug it into this formula. So you're going to do 1,000 times 1,000 plus 1 divided by 2. It's going to be that simple, whatever that is. I'll let you figure that up on your calculator, okay? All right? And see, that's a whole lot easier than adding up that whole series of numbers there, okay? All right. What if you're going to do the sum of your squares? Okay. Then same concept. Let's say that you're going to do the summation as I goes from 1 to 1,000 again of I squared. Well, that means 1 squared plus 2 squared plus 3 squared plus all the way up to 1,000 squared. You see these numbers are getting a lot bigger, right? So again, this is your n. You would plug it into this formula, and you would do 1,000 times 1,000 plus 1 times 2 times 1,000 plus 1, and then every bit of that is divided by 6. Okay? And then whatever you get there, okay, you just put all that in your calculator, okay, and you would just add it all together. Okay? So I think you're getting the idea here of what the summation means, okay? And so you would follow that same little pattern right here with the sum of your cubes, okay? Notice that the sum of your cubes looks a whole lot like the sum of your integers, except for it's the sum of your integers squared, okay? Just a quick little way for you to remember that formula, okay? And yes, you do have to know those formulas. You will not be given those formulas, okay? So this is example 2 in your book. That is on page 254, okay? And I'm going to go through that example with you and show you how we use this, okay? That example says to take this summation and to evaluate it when n is 10, 10,000, these numbers, for some reason I can't talk, 10, 100, 1,000, and 10,000, okay? Well, the main thing to remember here is that n is a constant number. It does not change, okay? Because it has commas between it right here. It says, you know, use this formula when n is 10. Do it again when it's 100. Do it again when it's 1,000. Do it again when it's 10,000. So I could actually use this formula here 4 different times. Or what I could do is I could use all the formulas that I just went over, and I can simplify this down to give me an expression which it would be easier to find the summation. This is what I'm talking about, okay? We're going to use those formulas that I just showed you here. All right, keeping in mind that n is a constant number. It's not changing, okay? I'm going to pull this out as a scalar. So I'm using that very first property about having a scalar here, okay? So I'm going to pull that out in front of the sigma and make this an understood 1 over n squared. Ooh. Okay? I is the variable because it is what's changing. It's going to be 1. Then it's going to be 2. Then it's going to be 3, 4, right on up to whatever n is. Okay? All right? So when I pulled the 1 over n squared out, I was left with I plus 1. Okay? The next thing I'm going to do is apply my second property. And I'm going to give that I and this 1 its own summation. So 1 over n squared, put all that in brackets or parentheses, whatever you want to use, of I equals 1 to the, as I goes from 1 to n of I, and then plus the summation as I goes from 1 to n of 1. So that was applying your property, your addition and subtraction property. Okay? All right, now I'm going to apply some formulas that I learned just a while ago. Okay? My first formula is this. Isn't this the sum of your integers right here? Okay? So what that means is I'm going to write the formula for the sum of my integers, and that is n times n plus 1 all over 2. All right? And then this one right here, this is the sum of a constant, because 1 is just a number. That 1 does not have an I in it. Okay? So it's just a number. It's a constant. All right? So what I'm going to do is apply my formula that says all I have to do here is multiply my constant times n. and that gives me n. Okay, notice that when I apply my formulas, the sigmas are gone, okay, because this is the sum of all my integers, 1 plus 2 plus 3, and so on. This right here is the sum of 1 n times, okay? So I've already done what sigma told me to do, and now all I have to do is to simplify this formula, okay? So what this gives me here is 1 over n squared times n squared plus n, and that is all over 2 plus n. We get a common denominator right here, okay? And my common denominator, okay, is going to be 2. So that's n squared plus n plus 2n. And combine my like terms. And I'm going to multiply. Actually, I'm not. I'm going to factor out an n right here. The reason I'm doing that is because this fraction has an n on the bottom, and I can cancel this n with that n. And now I can just multiply across the top. 1 times n plus 3 is n plus 3. And then n times 2 is 2n. And this is actually what we call the sum of n, okay? S of n. So now I can do the second part, okay? Now I can evaluate this for those 3 values. They told us to evaluate it for 10, 100, 1,000, and 10,000. And I can do this without a calculator. I haven't picked up a calculator yet, okay? So that's going to be 10 plus 3 over 2 times 10. So that gives me 13 over 20. And then I can put 100 plus 3 over 2 times 100. So that gives me 103 over 200. And then I can do 1,000 plus 3 over 2 times 1,000. So it gives me 1,003 over 2,000. And then finally I can do 10,000 plus 3 over 2 times 10,000. And that will give me 10,003 over 20,000. Do you see what's happening to these numbers right here? They're getting bigger and bigger and bigger, right? Okay, keep that in mind, okay? All right, next thing, okay? Know the area of geometric figures that are on page 255, and I do want to add one to that, one particular formula, and that is the trapezoid. Make sure you know that formula as well, because we're going to be using that, okay? Now, I just want to go through some examples to show you how to use those formulas a little bit better on page 261, okay? I'm just going to do these 4 problems, I think. Yeah, okay? Look at problem 2 here, okay? In your book, it says use the summation capabilities on your graphics calculator, okay? You do have the summation on your calculator. If you go to Math, and then you scroll down to 0, then you will see what says summation, okay? And when you click on that, then what you're going to get is an output that looks like this, okay? You have a sigma and you have, not that, okay, you have a little box here, and there's a box here, and then there's a box here, and then you have parentheses with a box right there, okay? What you're going to do is you're going to always tell them what your variable is, and in number 2, the problem says to figure out the summation of k as it goes from 3 to 6 of k times k minus 2. Okay, so what you're going to do is just put a variable here. Now you can actually use k if you want to, but I would just use an x. I would say I'm going to let x go from 3 to 6, and then right here in this box I would put x times x minus 2. Okay, you do have to make sure that those right-handed parentheses are there. Let me draw that a little bit better, a little bit bigger for you so you can see it better. Okay, so when you put that in your calculator, you're going to do x times x minus 2. Okay, of course that box is going to go away, but you will have left-handed parentheses and left-handed parentheses, right-handed parentheses there. And when you put that in your calculator, it will tell you that your sum is 50. Okay, so that comes in handy a whole lot if you have access to a calculator. Okay, all right, let's look at number 16. Okay, just to go through those formulas with you a little bit more. Okay. Number 16, it says to use your properties and your formulas for summation to simplify this expression. The summation as I goes from 1 to 15 of 2i minus 3. Okay, notice with all your properties and your formulas that I has to start at 1. Okay, so what I'm going to do is to this term right here, I'm going to apply the fact that I have a scalar in front of I, and I'm going to rewrite this as 2 times the summation as I goes from 1 to 15 of I. So I brought the 2 out as a scalar, and now this is just a constant, so I'm going to bring down my minus sign and give the 3 its own sigma as well. So the sum as I goes from 1 to 15 of 3. Okay, so now what I've done is I've set myself up to just plug in my formulas. Okay, so right here what I notice is I'm doing 2 times the sum of my integers. So 2 times the sum of my integers, that formula is n times n plus 1 all over 2. And then minus, this is the sum of a constant. So the sum of my constant says just to take the constant and multiply it times n. Okay? Now, all you have to do is fill in what n is. Well, n is 15. That's the number you stop at. Okay? That's the number of terms that your series has in it. All right? So this is going to be 2 times 15 times 15 plus 1 over 2. Notice that it was just this one that was multiplied by 2, not the whole thing. And then minus 3 times 15. Okay? And then we'll simplify. I'm going to cancel those 2's right there. That just gives me 15 times 16 minus 45. And I know that 15 times 15 is 225. I need a 16th 15, so that gives me 240. Okay, and so I end up with 240 minus 45, and that's going to give me 195. I did all that without a calculator. You can too. Okay, all right, let's take a look at number 20. Okay, number 20 says that we are going to do the summation as I goes from 1 to 10 of I squared plus 1. I missed that. It's I. There's an I times I squared plus 1. Okay. What I would do here is what I've always told you to do. Okay. Simplify everything before you try to apply a formula, whether it be limits, differentiation, integration, summation. So let's multiply this out and make it I cubed plus I. We just made that problem a whole lot easier. Because all I'm going to do now is I'm going to apply my formula for the sum of my cubes as I goes from 1 to 10 plus the sum of my integers as I goes from 1 to 10. Okay, so my formula here says I have to do n times n plus 1 times 2n plus 1 all over 6. That's my formula for the sum of my cubes plus the sum of my integers is n times n plus 1 all over 2. That is not the sum of my cubes right there. Why'd y'all let me write that? Let's try that again. That's the sum of my squares. My sum of my cubes is n times n plus 1 all over 2 squared. There we go. All right. N is 10. That's the number you're going to. That's how many numbers are in your series. So 10 times 10 plus 1 all over 2. We're going to square that. Plus 10 times 10 plus 1 all over 2. Okay. Well, that's 10 times 11 divided by 2. Or, to make it a little easier, you can say, well, I'm going to cancel that 2 into that 10, make that 5. That becomes 5 times 11, which is 55, squared. And, of course, I just figured out that 10 times 10 plus 1 all over 2 is 55, right? Okay. All right. Now you can, do 55 squared and then add 55 to it and all that stuff if you want to. Look how easy it is to come over here and multiply, y'all. It's so easy to multiply. I better get this right telling y'all that it's easy, hadn't I? Okay. And then I'm going to add 55 to that. Okay. And that gives me 3,080. Okay. So yes, you can do this without a calculator and not die. You can actually survive it. Okay. All right. Last one, number 36. Okay. 36. This one is similar to what we just did. It says that you're going to do the summation as, I'm going to change that J to an I, as I goes from 1 to N of 4I plus 3 all over N squared. So this is like that very first example that I just showed you where you don't have just I in here, but you actually have N in this expression as well. Keep in mind that N is a constant. So I'm going to pull that 1 over N squared out as a scalar. Okay. All right, so it's gone. And then I'm going to separate 4I plus 3 using my properties, okay? I'm going to pull 4 in front of the summation. And then I'm going to give the 3 its own summation. Okay. I'm going to apply my formula to this summation. So 1 over N squared. That's going to be 4 times the sum of my integers. 4 times N plus 1 all over 2. And then the sum of a constant is the constant times N. Okay, I'm going to simplify. This 2 divided into that 4 leaves me with 2. this is going to be 2n times n plus 1, which is 2n squared, plus 2n plus 3n. Okay. You probably could do this step in your head, but they all have an n in common, don't they? I'm going to factor out a 2n from there. This is actually 5n that I'm going to factor out the n. And then this n can cancel with that one, and I'm left with 2n plus 5 all over n. This is your S of n. Okay? And then from there, you're going to do like I did in the other example, and you're going to plug in 10, and then plug in 100, and then plug in 1,000, and then plug in 10,000, and so on. And what you get is a number that is increasingly getting closer to what number? Exactly, it's getting closer and closer to 2. When was the last time we talked about something approaching a certain number or getting closer and closer to a certain number? I know you're getting excited because more and more it's beginning to sound like a limit. Yes, it is, okay? All right, we're not going to do limits yet with this, okay? But it's coming. Be prepared, all right? Next thing I want to go to is something a little totally different, okay? And that is Reimann sums, okay? And like I said, you know, when we get to 4.3, we're going to put everything together that we've been learning in 4.1 and 4.2. You're going to see how all this comes together and what it means, how it relates, okay? So you just be patient with me as we build on this, okay? All right, so a left Reimann sum. What in the world is that, okay? Well, we're going to use what's called a left Reimann sum, and we're going to figure out what the area under this curve, x squared plus 2, which is a parabola, on this closed interval from 0 to 3 is, and we're going to use 3 sub-intervals, I should say, of equal width, okay? Your sub-intervals are not always equal, okay? But for what we're going to do here today, they will be of equal width, okay? All right, so let's get going on this. All right, first thing we're going to do is we're going to graph this function on this interval. Just plug in your numbers. Plug in 0 and you get 2. Plug in a 1 and you get 1, 2, 3. Did I put that on the right line? I did. How did that scoot over? I don't know how that happened. I think something happened there when I saved the file and reopened it. Hold on. Okay, so this is what I wanted. This is 1, 2, 3. I'm just making these units a little bit bigger because I want you to actually have some room to see some stuff that's going on. Okay, but my units on my y-axis, I'm still going to keep those at 1, but on my x-axis, I'm going to make them a little bit bigger. I'm going to spread them out some, stretch them, okay? All right, where was I? Okay, now, if I let that be 2, then that's going to give me, what, 6? 1, 2, 3, 4, 5, 6. And if I let that be 3, that's going to give me 11. 1, 2, 3, 4, 5, 6, 8, 9, 10. Okay, so this is what my curve looks like on that interval. Okay, all right, so it wants us to take that curve right there and do what we call a left side Reimann sum of 3 sub-intervals. Okay, well, this is the first point A, the left endpoint of my interval. This is the right endpoint, B. What we do to figure out what our width is going to be is we're going to do B minus A, and we're going to divide by n, where n is the number of our sub-intervals. So we're going to do 3 minus 0 and divide that by 3, and I know that my width for each rectangle is going to be a 1. Okay? So when I do that, all right, that means that I'm going to be drawing some rectangles under this curve where the width is just 1. And the left top point of that rectangle is going to be on the curve. So starting right here, I know I want to put a rectangle in here somewhere. Okay? And the way I'm going to draw it is I'm going to draw my rectangle such that the left end point is on the curve. So if this is the left end point of my rectangle, I'm just going to go straight across here, and that is the rectangle that I am looking for. Okay? Now I'm going to do the same thing here. I have a width of 1, and I want to draw a rectangle right in here such that the left end point is on the curve. Well, this left end point right here is on the curve if I draw the rectangle across here. Okay? And then I'm going to do this again. The last time, because I'm only going to 3. Okay? So I'm going to draw this rectangle right here, or draw that line right there to separate my third subinterval. And I want a rectangle in this area right here such that the top left point of my rectangle is on the curve, and that would happen here. So these are the rectangles that I'm looking at. Okay, so this is what we refer to as a left side Reimann sum. Okay, and that is where you draw rectangles under your curve, and the left top point is on the curve. Now what we're going to do is we're going to figure out the area. Well, this is what I call area 1. This is area 2. This is area 3. And what we do to get that area is we just add those 3 areas up. And we're just estimating using rectangles what the area under the curve is. Okay? So my area, okay, is going to be this. The area of the first curve is going to be the width of my rectangle, which is 1, times the height of the rectangle. Well, the height of the rectangle goes up to right here, which is 1. Okay? But we're going to use function notation to represent that ordered pair. Right here, that ordered pair says that if x is 0, then y is f of 0. Yes, use function notation. You're going to love me when you get to the AP test and you know how to use function notation. Okay? Alright, so let me write this a little bit better. So that's 1 times f of 0. Alright, so that is the width of this rectangle times the height of that rectangle. Length times width gives us the area, right? Okay? Now, second rectangle, the width is still 1 times the height of this rectangle is right here, which, yes, I know that height is 3, but in function notation, 3 is the same thing as f of 1. And then this rectangle has a width of 1 times its height would be what? Yes, f of 2. Okay, and that's how you write that in function notation. Then you can come back and fill it in. You can say, well, this rectangle is 1 times whatever f of 0 is, okay, which is 2. Remember, I was just counting by ones on the y-axis, okay? And then this one is going to be 1 times f of 1, which is 3, plus 1 times f of 2, which is 6, and that gives me an area of 11. Okay, so using a left Reimann sum, there's approximately 11 square units under here. Now, I know that that is actually a lower estimate. This is what we refer to as a lower estimate. And it's not because it's a left estimate, okay? Do not think that left means lower. That is not true, okay? Left does not mean lower estimate. This is a lower estimate because this function is increasing and all of my rectangles are under the curve, meaning that what happened when I estimated is I actually have this area right here that didn't get included in my estimate. So that makes my estimate lower than what the actual area really is. And that's why we refer to it as a lower estimate. Okay? Now, let's do the same thing here with the right Reimann sum. So real quick, I'm going to plot these points and make this graph again. Okay? And I put that ordered pair in the wrong place. There we go. Okay? Alright, going to do the same thing. We're going to have 3 sub-intervals from 0 to 3. Still put it in the wrong place, didn't I? Get going, Miss Letchworth. Okay? There we go. Let me see if I can make that prettier. It's okay. Y'all get the idea, don't you? Okay? Alright? So this is what we've got going on here. Alright, this time it's going to be a right Reimann sum. That means the right endpoint has to be on the curve. So, if I'm looking at this interval right here, and I want to draw a rectangle, then I'm going to use this side, and the right top endpoint has to be here, meaning I've got to come across like that. I'm going to use a totally different color here. Okay, so I'm using this side right here, but I'm going to come across right there. This is going to be the rectangle because that's the rectangle whose right top endpoint is on that curve. I'm going to do the same thing here. I want to draw a rectangle whose right endpoint is going to be on the whose right top endpoint is going to be on the curve. So there's my rectangle. With this subinterval, that's going to be a long rectangle. Here's my top right endpoint. Come across, come down. And these are the rectangles that I'm looking at right here. So these rectangles are the ones whose area I want to find. Okay? I'm going to do the same thing with some function notation. Alright? Okay, I'm going to say for this area that the width is 1 times the height, which is f of 1, plus the width of this one, 1, times the height of this rectangle is actually f of 2, plus this rectangle, the width is 1, times its height is f of 3. So that's going to be 1 times 3 plus 1 times 6 plus 1 times 11. And that is going to give me an estimated area of 20. Okay? Alright, notice that these rectangles were on top of the function. Okay? For that reason, we call this an upper estimate. That's because all of this area right here that's in the rectangles but that is above the curve, it's not included beneath the curve. So we actually have an overestimate or an upper estimate. Okay? They don't get too picky over which word you use, upper or above, or upper. What was that other word I just used? Darn, I just forgot. I don't remember. Bigger estimate, upper estimate. Okay? Overestimate, that was the word, okay? Now, what happens is a lower sum occurs when you're trying, so your rectangles are inscribed. Inscribed means your rectangles, every single part of your rectangle is beneath the curve, okay? Circumscribed, it's going to give you an upper sum. That means all your rectangles have a little bit of, part of the rectangle is above the curve. okay? So, for instance, what you're seeing right here is an increasing function. Let me show you what this looks like if it were a decreasing function, okay? I'm just going to sketch something. It's not going to be perfect, okay? All right, but let's say that you had a decreasing function. Here's a function that's decreasing, okay? And you were to do inscribed rectangles, okay? If I wanted an inscribed rectangle, do you notice how this is actually going to be a right Riemann sum? And the reason it's a right Riemann sum is because all the right endpoints, right top endpoints are on the curve. Okay? So this is a lower example of a lower sum that is a right Riemann sum. That's why I told you a while ago, do not think that left means lower. It's just not true. Okay? And like here, an upper sum, that means that your rectangles, okay, when you draw them, part of your rectangle will have to be above, okay? So there you go, right there. Do you see how I'm doing that? It's not very pretty, but I'm doing it. Here, let me try it this way. There we go. All right. So do you see how when I did these rectangles right here, they're above the curve? But look at what point is on the curve. It's the left top point. Okay? So this is an example of an upper sum that is a left Riemann sum. Okay? So left does not mean lower. Do not confuse that. Okay? Real quick, let's move on. Okay? Let's do midpoint and trapezoid. Same function, same intervals. Okay? So let me sketch those real quick. 0, 2, 1, 3, 2, 6, and then 3, 11. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay. All right, so the midpoint Riemann sum. Okay. We're going to separate this into 3 intervals. And this time when we draw a triangle, I don't know why I keep calling it a triangle, a rectangle, we're going to draw our rectangle such that the midpoint of our rectangle, at the midpoint of the top of our rectangle is on the curve. Well, this is the bottom of my rectangle. In the bottom of a rectangle, the same as the top, okay, the same width. So here my midpoint is 1/2. So I'm going to come right here and I'm going to put a point there. Here my midpoint is 1.5 or 3/2. I'm going to put a point there. And here my midpoint is 5/2. So I'm going to put a point there. Okay? So when I draw my rectangle, what I need to do is make sure the top of it goes through that midpoint. And here are my rectangles. Okay? Alright? And this is the area that we're looking for right here. Okay? So, again, what I'm going to do is I'm going to say that my area is equal to a width of 1 times my height, which is 1/2, f of 1/2. Okay, plus this width of 1 times the height of this rectangle, which is 3/2, f of 3/2. And then 1 plus f of 5/2. Okay, now I know you're looking at that graph and thinking, oh, how am I going to estimate that? Well, you really don't have to. You know the function. So you could just plug in a half into this function, then 3 halves, and then 5 halves. So 1 times f of a half, if I plug in a half right here, I get 2.25. Yes, I am actually double checking that. Okay, 2.25. And then I'm going to plug in 3 halves, which is 4.25. Then I'm going to plug in 5 halves, which is 8.25. My estimated area is 14.75. Okay. All right, trapezoid. Well, same points. Let me put those in there real quick. Okay, same function, same subintervals. This time I want trapezoids. Well, a trapezoid has parallel bases. So I'm closing it up like this. Y'all see with each Riemann sum, we're getting closer and closer to the most accurate area. I'm going to erase this because I need some room. Okay, see, this gave us a little bit more of an accurate description of the area. This is getting us even closer. Okay, now be careful with this. Okay, the area of your trapezoid is 1/2 height times base 1 plus base 2. Okay, all right. So, rotate your trapezoid around, and it kind of looks like that. That's how you're used to seeing it. But rotate that and look and compare it to this, okay? And you'll see that your bases are the parallel sides, okay? So these are actually your bases right here, and the height is actually how tall these are. It's actually the same as your width right here. Okay? So the height of your trapezoid is this width, and your two bases would be these two segments right here. Okay? So let's do the first area here. We're going to have 1/2 times our height, which is 1. Speaking of, won't I do 1/2 times this height for each one of these three? So what I'm going to do is I'm going to kind of factor out the 1/2 height, and I'm just going to focus on the base 1 plus base 2 for each one of these trapezoids, okay? Looking at this first trapezoid, base 1 is the length of f of 0. And base 2 is the length of f of 1. Second trapezoid, you see I'm still going to do 1/2 this height, which is 1. That's why I was factoring it out. Now just do this base plus that base. Well, this base is f of 1. Whoa, I just hit the wrong arrow. There we go. Plus this base, which is f of 2. And now we're going to do this one, which is going to be f of 2 plus this base, which is f of 3. Okay? Now, before we plug in those numbers, I want to show you something. All of this is being added together. Okay? do you see how the endpoints of our interval was only used one time? I've only got f of 0 and f of 3 in there one time, but all of the middle segments got used twice. That'll help you out a little bit, okay? So you could actually have written this as your f of a, your first endpoint, plus 2 times f of whatever your next interval is, your next point that divides your intervals is, plus 2 times f of 2, because they're going to be used twice. So those inside segments, they get used twice. The outside ones only get used once. Okay? All right? So area equals 1/2. 1/2 times 1 is 1/2 of f of 0, which is 2, plus 2 times f of 1, which is 3, plus 2 times f of 2, which is 6, plus f of 3, which is 11. And when you simplify all of that stuff, okay, then you get 1/2 of 31, which is 15.5. Okay? All right. Last two problems here. All right. Page 32. I'm sorry, page 262, number 32. All right. It says 32 gives you that S of n is equal to 64 over n cubed times n plus 1 times n plus 2. I'm sorry, 2n plus 1. I make this stuff up sometimes, about like y'all do sometimes on quizzes and tests. I'm just kidding. Okay. All over 6. Maybe you'll recognize that formula right there. Some of your cubes. And it says to find the limit of S of n as n approaches infinity. Okay? So I'm doing the limit as x approaches infinity of all of this stuff. 64 over n cubed times all of that. Remember, everything we're doing in 4142, we are laying a foundation for something major in 4.3. So you have really got to understand this stuff, okay? All right, before we take a limit, what do? Dun, 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 we simplify, okay? Here we go. Let's simplify 64 over 6. Divided by 2. Okay? This n over divided into that's going to leave me n squared, right? Okay? So what I'm going to be left with is the limit as x approaches infinity of, let's bring that 32 over 3. Let's bring that out as a scalar. Let's see what we're going to have left. Okay, so I just brought that out. I just brought that out. That is actually a power of 2 right there. That's not a scalar. So I'm left with n plus 1 times 2n plus 1 on top. So if I multiply that out, I get 2n squared plus 3n plus 1. And on the bottom, I get n squared. Okay? I put as x approaches infinity, y'all. Let's stick with the n's here. Sorry, my bad. Okay? Alright, well, y'all know how to do this. Limits to infinity. This degree is the same as that one. 2 over 1 is 2. And if you blinked, you just missed figuring out what that limit to infinity is. Okay? Times 32 over 3. So the limit as x approaches infinity of S of n is equal to 64 over 3. Okay? Now, number 40. Okay? It says to figure out the limit as n approaches infinity of the sum as I goes from 1 to n of 2I over n times 2 over n. Okay? So this is the limit of the sum. Okay? Now what I'm going to do is I'm going to remember that you can only eat an elephant one bite at a time. Okay? So I'm going to take this step by step. Alright? And I'm going to do the sum of all this first. So I'm going to be carrying this limit down for a couple of steps here. Okay? And I'm going to simplify this. Well, remember, what's changing? I. Because I is 1, then it's 2, then it's 3, all up to n. N is constant. Okay? What I notice is that I can pull this 2 over n out and this 2 over n out as a scalar because n is a constant number. Okay? So that's actually going to be 2 times 2, which is 4. N times n, which is n squared. That's going to come out of this sigma. And I'm just going to be left with I. See where I'm going with this? See, we know this formula right here, don't we? So I'm taking the limit of all this. And what I'm going to go out to do is to plug in my formula for that. So the limit, yes, there is a purpose behind this, I promise. You just got to learn how to do this, okay? Please just stick with me. So 4 over n squared, my formula for the sum of my integers, n times n plus 1 all over 2. Simplify before you take a limit. See, once I plug in this formula, my summation's gone. So now I'm going to simplify before taking a limit, okay? 2 divided into 4 is 2. This n cancels with one of those, okay? That is all that I see that I can cancel. So the limit as n approaches infinity of 2n plus 2 all over n. Now your limit to infinity, these degrees are the same, so that limit is simply 2. And like that, we are done.